All right, so we've estimated the value of this probability of a site being adjacent. And so at this point, we can kind of plug in everything and see where we're at in terms of diffusivity. And I want to start with the interstitial. So the diffusivity of interstitial. And we're basically going to plug in everything we know about that material. And so we have alpha for an interstitial, lambda squared, and then we have our omega term, which was related to nu, so nu not exponential of minus delta H of the interstitial, and then this is over KT. So again, because our value up here was close to 1, so we are basically, that's why you don't see it here. So we just have omega represented by nu, and then there would be multiplied by 1, so we just got rid of it. And then we have alpha and lambda squared. And again, in this specific case, this is the activation energy needed for an interstitial to jump from one interstitial to the next. So that's why we kind of put the additional subscript there. So let's look now at a vacancy. So for a vacancy, so the jump frequency is increased by the number of atoms that surround the vacancy. So we have to know this vacancy coordination number, which again was the squiggle xi in the notes here. I will say I had trouble getting the right symbol here. So you should see something similar to this. Again, I apologize, it doesn't look perfect, but to me it's very hard to get the number of squiggles right. It should actually be zeta, but I could only get a certain notes here. So just make sure you know that that's the vacancy coordination number. And so that means that nu for vacancies is equal to that coordination number times the expression for the probability, because again, the probability of these jumps is going to be related to this. So basically, this is substituting in for what we have here. So it's close to 1, but we can represent that by the coordination number. Okay, and again, that was just for this expression. We're also going to incorporate this into the omega. So it's still multiplied by the roughly 1. And so when we plug in everything, we're going to get the geometric constant alpha, the squiggle term, lambda squared, mu naught exponential of this term that we've seen before, and this would be multiplied by the approximate 1. So this factor, this coordination factor, is strictly for the energy calculation. And then we also have theta. I misspoke a bit earlier. So theta we're still saying is approximately 1, because most of those vacancies are surrounded completely by atoms, because we have a very low amount. Okay. So now I want to, we've talked about vacancies, we've talked about interstitials, so we've got expressions for 2 of the 3 so far. And so let's look at atoms, ions. So here, the diffusion species is the atom or ion, and the vacant site is an actual vacancy in this case. And so again, the number was very low, as we talked about. And so this probability of the site being empty is going to be equal to the mole or site fraction of vacancies, right? This is what we did in the previous chapter on defects and Brauer diagrams and so forth. So basically the site fraction of vacancies, we used a term maybe like this to represent the site fraction. Here, we're going to call this uppercase lambda. And so we can, omega is effectively going to become lambda, or sorry, theta times the new term for vacancies. And if we write out the diffusivity for an ion or atom, it's going to be alpha lambda squared, and then this site fraction of vacancies multiplied by this, right? And so we have that squiggle term again, nu naught exponential of this. So in essence, we can closely relate the diffusivity of an ion to the vacancy, and really, if you're kind of looking and following along with these two, the main difference, the only difference, is the factor of this, which is the mole or site fraction of vacancies. So that's the modification to it, because that tells us basically this term right here. And so that's where we get all of this. And so this is kind of our deriving these diffusivity expressions to try to get from an atomistic view of what's actually happening and where these terms come from. So in the next videos, we're kind of going to put all this together and see if we can relate this back to that experimental view of diffusivity and relate them together.